chapter 9.3, analysis of paired samples. Still, we are talking about paired samples. If you remember, we consider two populations, then take two samples from those populations. They are independent. We call X and Y. So those we call paired samples. So we still check their means. They are separate their means. We compare whether this mean whether there is a difference between these two means, something like that. Not individual values, but we compare them based on our hypothesis test. As I mentioned here, in in section 9.1 and 9.2. In your note, you can see just 9.1, but in the section 9.1, that note, it includes 9.1 and 9.2. I think 9.2 is the pool t-test part, okay, which I did last day. So we did the inference about difference between two means, mu1 and mu2. But in some cases, we have to consider natural pairing of values. Like still they are like two samples, but situation is like this. For an example, like I measure my weight today, and again I measure my weight a week after today. You can see still I'm measuring my weight, so still it's me, but you can see there may be difference between those two values, something like that. Same person but different values. So that kind of things we call natural pairing of values. Still they are like two values, but they belongs to a same like they belongs like same sample, something like that. Okay, like this, first value and the second value. Okay, so this kind of things, pairwise hypothesis testing, we are discussing in this section 9.3. Okay, so paired samples, these kind of paired samples, still they are paired samples. Okay, I mean they are paired samples, they are like a pair, two things. So having I think these are examples. Yes. Okay, check this one. This example, having medical results, test before and after the particular treatment. Okay, same person, two different measurements. This one, score, test before and after the this means I think final test. Okay, score before and after the test. Same thing here, having some opinions of married couples before their marriage and after their marriage. So sometimes that before measurement and the after measurement, they are similar sometimes. So there is no difference between those two. That can be happen. Okay, temperature of house inside and outside. Okay, so as I mentioned, sometimes they have like they are different, but sometimes they may not. Like let's say this is sorry, indoor is 90 Fahrenheit, then again this can be 90 Fahrenheit. It's also possible, but you can consider it as a pair. Okay. Okay, assumptions, they are very similar to the assumptions what we made sorry, in this chapter. This data consists of n independently pairs. I mean there are n number of samples. Okay, each sample has two values. Previous last time we had something like this. This is your two populations and this is your samples. We call this capital X, this is capital Y. They are totally independent, right? But now what you have is something like this. You have a sample, but that sample is like this. It has two values. This is your X, this is your Y. Okay, they are like pairs. Okay, so as you can see here, those pairs like x1 y1, x2 y2, x3 y3, something like that. Okay, this y denotes the second observation. This denotes the first observation of each pair. Okay, so if I write it like this, it will more clear. So this is going to be first observation of the first sample, x1 y1. Second sample, x2 y2. Okay, so likewise xn yn. Okay, so you can consider they are like two individual observations. Okay, since we are considering same person or thing, we just paired them. But in general, you can see that those x's and y's, those values are not independent. Let me check the question. Yes, do you have any questions? Did you check, aren't there any notes of this section? Haven't I uploaded it? Okay, that's fine. Okay, if it is not there, I will upload it today. Okay, I think right after the class I'll upload it. Okay, I think I assume that it's there, so I'm so sorry that I'll upload it after the class. Okay. Oh, sorry. Oh, okay. Okay, I will upload it right after the class. Okay. In general, as I mentioned, in general, you can see that they are not independent. Like my weight today and week after, they are like not simply independent, right? It's still me. But in this case, we are considering that they are independent and they are normal distributed. They are normal distributed. Yes, that can happen because my weight is normal distributed. Then after a week, same thing, normal distributed. It doesn't matter. But sometimes there's a problem because these pairs are not independent. Okay, but in this case, because of that, we consider not x and y's. We consider those pairs are independent. Those pairs are independent. Simply we call those pairs samples. Each pair is a sample. Okay, that's the word we use in general. Okay, or observation. So these are the pairs. So you can find the expected value of this column, expected value of this column separately. Okay, because these are just values. Expected value of xi's, it's mu1. Expected value of yi's mu2. Okay. Difference between these two values, if you consider one pair x1 and y1, you can find the difference between these two values, x1 minus y1. We denote it by di, d. Let's say this is d1. D mean distance between those two, or simply once you subtract x1, y1 from x1, that's the d. Normally we call d. Okay, that distance, that gap. So di mean any pair, difference between any pair. Di's are assumed to be normal distributed. As I mentioned, if, where I can write it, if my x is normal, let's say my x is normal distributed, okay, with mean and mu, with mean and some variance. My y's are normal distributed with some mean and variance. Okay, so if you remember, I told you they are summation x plus y. It also has a normal distribution. Okay, same here. Their difference it also has a normal distribution. That's why we have assumed that di has a normal distribution. It is normal distributed. Okay, their difference has a normal distribution. The reason is individually these guys, they are normal distributed. Okay, so that they have mentioned that normal distributed di's mean is mu d and variance is sigma d square. Okay, them say, yeah, xi's and yi's, they are normal distributed. That's the reason. Okay, clear? Okay. Simply you can calculate this mu d by taking expected value of xi minus expected value of yi. But variance, what happened? If you consider the variance, if variances are adding together, you had, like, if you remember, plus adding together minus. Yes, plus. What happened variance? What do you think when variances are subtracting? What will happen? If those x and y are independent, then same thing happen, because only difference is that variance x comma y, variance x plus variance y. The rest of the part, I told you, when x comma y is negative, covariance part. So covariance 0, same thing happens. Okay, so you can calculate that. I don't think you need that, but just a note. Same here, we throughout these sections, starting from chapter 8, we state our null hypothesis, then alternative hypothesis. So same here. Here we just focused on their difference. This is exactly same. I think chapter 9.1 is stuff. We consider mu1 minus mu2. Same here, because what is this mu d? Mu d is mu1 minus mu2, right? That's we call mu d, right? So here we consider this difference mu d. Always null hypothesis equals to something. This can be 0 or any value. Okay. According to those three scenarios, it can be not equal, greater than, or less than. Okay. Sorry. This mu d mean, again, this one. They are mean difference. See. Okay. But I mean, since we are discussing these paired samples, we in general we use mu d. In general, we use their difference. Okay. Test statistic. It is exactly same as what we did in chapter 9.1. Only difference is this guy right here. Last time we had like mu1 minus mu2. This is still same, but using different notation. Okay, d bar here because of this mu. Okay, you can calculate this one by taking all the di's. Summation of all the di's 1 to n divide by n. You can get your d bar. Okay, I'll show you what is this d, which mean your x1, y1, or x1, x2, that's fine. Xn, yn. You can calculate this di, which means gap between those gap between each pair, x1 minus y1. Likewise, xn minus yn. After that, you can add those these differences, these values, sum, and divide by number of observations, number of pairs. Okay. So replace d bar from this value. This sometime is 0, Sometimes it is not. It based on your question. Okay, if they have mentioned that that distance, that difference greater than 5, then delta note is 5. There is no difference between those pairs, then that's going to be 0. Okay. SD again. What about this SD? You have to calculate this SD using what? This is sample standard deviation. Still, it denotes the sample standard deviation. So summation of, do you remember that equation? Summation to calculate the standard deviation, summation of xi minus something square divided by n minus 1. You have to use the same equation to calculate your SD. Okay, it is the sample standard deviation based on this column. Okay, based on this. So d bar is the sample mean of di. Yes, this one. SD, yes, it's also based on this one. Okay. Di mean their difference, pair difference. You have to use t table because most of the time we are dealing with a very small number of samples, so you have to stick with the t table. You can use critical value or pre-value approach. This time degree of freedom is n minus 1, same as general t-test. Okay, because you saw in chapter 9.1 and 9.2 we use different degree of freedom. Okay, 9.1 we calculate v using a giant equation, and 9.2 for the pool test we calculated the degree of freedom like summation of those two number of samples minus 2. Okay, but this case it's like just one sample case, so degree of freedom is n minus 1. Okay, because we have only just one samples. We consider x and y together. So we have to find the confidence interval as well. So hypothesis test, then confidence interval. Always 100% 1 minus alpha percent 100 1 minus alpha percent confidence interval. Here it's the paired t confidence interval. Why t? Because we are using t table. Why paired? Because they are pairs. Okay. Confidence interval for mu d. Mu d mean mu1 minus mu2. So only difference is, see, if you remember the general equation for to find the confidence interval, you have to replace this value right here and this one. All others are same. Since you are considering confidence interval, you have to use alpha over 2. So everything is pretty similar, but you have to replace those first value d bar and its standard deviation. Okay. You go to the t table, you can find, you know what is the degree of freedom? It is n minus 1. This is your degree of freedom. N mean number of samples. Okay. Or number of pairs. One side, what is this? One-sided confidence bound results, yes. One value can be this one, the other value can be this one. Yes, they have mentioned this here, relevant signs and replacing, because once you are finding like less than, which mean left tail test, you have to use negative value, but you don't need to use that. This guy right here control that negative positive, so you don't have to worry about the value, but definitely you will be having an interval like this. Okay, value here, value here. Okay, check this example. So you have pairs, see, 1 2 3 4 5 6. Okay, so your n is what? N is 6 because you have 6 number of pairs. Before, after, many highways is about highway accidents, I guess. Yes, the signs typically does not provide information of the distances. So 6 sites, yeah, that's the number of samples. For each site, crash data were obtained from the 3 years period. Doesn't matter about the period. This is this gap between these two, before and after, it is 3 years. Okay. I was able to service sign and for 1 year period afterward. The number of okay, the number of crashes per year before and after signs change as as follows. Okay, at 5% significant level, test whether, okay, significant level alpha given, test, this is the researcher's claim up to this point. Test whether there was any change in the mean number of crashes before and after the addition of the distance between distance information on the signs. There was any change. There was any change. So what does that mean? It's going to be one tail or two tail. Any change mean two tail. Yes, it is two tail, which means not equal. Crash before and after. So you have to mention, first of all, you have to mention what is your mu1, what is your mu2. Then you can say, okay, mu d is this. So mu1, I'll consider mu1 is mean crash of, mean crash before. Mu2 is mean crash after. Okay, simply. Right? So your H naught, definitely null hypothesis is what? Mu d, oh sorry, you have to mention what is mu d. Mu d is mu1 minus mu2. So your mu d is definitely equals what? Now what? Now what about this guy, delta naught? Any change? So do we have a value for that? No, just any change. So this is going to be 0. Any change? If it is change, yes, it will there. But your HA is going to be like, I think it's in the next slide, you can see it. Mu D not equal 0. Yes, any change. So they have mentioned mu1 minus mu2, but simply you can rewrite as mu D. Okay, mu D. Any change? See, they have mentioned. So there can be a change. They haven't mentioned that change is a positive value or negative value. We don't know that. That can be any value. So that's why not equal here, change 0. So this is once you just check this one. Once you simplify a little bit, you will see very similar thing. This is going to be like this, okay? Which means first the mean of the first observations and the mean of the second observation, there is no difference, right? So those accidents, it doesn't matter where it happened or how it happened, before and after, no difference. Okay, something like that. So you have to test this, but you have to assume that this is true, then use your equation, which means T equals D bar minus delta naught over SD over square root of n. Okay, so you need this differences. So you have to find differences between each pairs before and after. So this column right here is the difference D. Always start from first one, subtract second one. Okay, don't mix them in the middle of this process. So always before minus after. Before minus after, it is -1. Before minus after 2, something like that. After that, get the sum. This sum. So you can see negative, positive cancel, and what's the sum? This is going to be 25, 26, So this is going to be -2. This cancel 35. Okay, sum going to be 35, right? Divide by 6. 5.5 6.6 times 5 30 7 okay, yeah, 6 times 8 48, so it is 8. This one, this value, yes, this is correct. I just want to check it. Yeah, that's correct. Okay, so sum is 35. How you get d bar? 35 divided by 6 number of samples. Okay, summation of di's divided by n, which means this value. Okay, use that equation to calculate the standard deviation. Okay, summation of each, here not exercise, each di minus mu square divided by n minus 1. Okay, so you have to calculate this value, then replace here, this replace this value. What happened to this guy? It is equals to 0. Okay, clear? Because we don't have delta naught. Delta naught is 0. Calculate it and you will see that T cal value is, sorry, this is your T cal. T calculated value is this much. Once you can use critical value approach, that's the easiest way. So critical value for alpha 0.25. I think yes, it is 0.25. No, it is 0.5, right? The two tail cases, we just divide it by alpha divided by 2, right? Sorry. For the p-value case, we multiply that p-value by 2 and compare with the p-value, compare with the alpha value. So here, yes, it is alpha over 2 because it is two tail, okay, not equal. So that you will get alpha over 2, this 0.025, this degree of freedom, you will get this value. Why plus or minus? Because it is like this. These are the rejection regions. Okay, so this is negative 2.5, this is positive 2.5. Your value is 0.7, negative 0.7 somewhere here. Okay, so what happened? In between these two values, we do not reject H now. So based on that, you can give your conclusion. Okay. Sorry, this is exactly what I mentioned. Yes, result from retained relevant sign replacing. Yes, that doesn't matter. I'm so sorry, I just confused. I just forgot what we are dealing with. We are dealing with two tail cases. Okay. Thank you for that. Clear? If it is a one tail case, simply you can use alpha instead of alpha over 2. Okay. Okay, check this example. Yes. I think you don't. No, you don't have answer for this. I'll show you how to do this problem. These are the observations. There are 16 number of observations. This is your number of observations. Okay. So one mean okay. Elasticity obtained 1 minute after loading in certain configuration and 4 weeks after that configuration. Okay, so this is a pair, 1 min and after 4 weeks. So you can see those values. There are 16 samples. They have already mentioned the difference between each observations of a particular pair. Calculate and interpret 90% upper confidence bound. Okay, 90% upper confidence bound, which means what is your alpha? It is 100% 1 minus, sorry, 100 1 minus alpha percent, which means 10%. Alpha is 10%. Simply you can write it 0.1. Okay, so alpha is 0.1. I think this is another part. No, does that support? Okay, bound for the true average, which means what is true average? Mu1 and mu2. Two averages. Two average difference between 1 min module and 4 week module. So mean of this guy mu1, mean of this guy mu2. Okay, for this guy, for this one. Does that does the data support enough evidence on true average mu1 and between average between one mean module and 4-week modules is different at 10% significant level. Again, different at significant 10% significant level. Different. Are they different or not? You have to check it, which means this is a two-tailed test again. So you have to test it. Okay. Clear? Differences they have given. So you can find d bar, summing those values, divide by 16. Okay. You can find SD using using that equation. Okay. Then plug the values into the equation and simply you can find the tcal and then compare, give the final conclusion. Okay, this is how we deal with this kind of problem. You can see that starting from chapter 8 to end of this section 9.3, everything is pretty similar. Okay, like whether it is C test or T test, what you have to do, just plug the values into that equation, do the calculation, and finally compare them based on similar procedure. Okay.